Right. That's good. Now, why is Earth here? Who is Earth? Speak. I don't know who Earth is. But his mysteries we'll never know. All right, so anyway, this is the thermal class for materials. So it's supposed to be 25, 26 in here, right? 1, 2, 3, 4, 5, 6, 7, 8, 17. So I'm missing like 9, which is hard, I guess. Is there even room for 9 here? Like 1, 2, 3, 4, 5, 6, 7, 8, 9. There's exactly room for 9. Oh, I guess there's like 11 on the side. Anyway, so there's a web page for this class. Let me hide this thing. Yeah, right here. So to get to that web page, what I did, I typed my name. If you have to figure out how to spell my name, Beaucage, and then I just put research group because that's kind of the name of this web page. And then it comes up. It's like the first thing here. And then the class is like the top one here. Just click that. Or you could write down all this code thing here. So either way. And this used to be there was only one Beaucage in the world on the internet, you know, but now there's like more and more. It's pretty weird. So my daughter's in LA and she just like, she goes to a dentist and they go, oh, you're recommended by your relative, you know, because there was another Beaucage. And it's like so odd, right? And it turns out she Googled it and there's a Beaucage. They're all from like Canada, from Montreal or something, right? And half of them are like American Indian, the other half are hockey players. There's a couple people that somehow got into science. So there's like one that's doing some kind of spinal something or other you can find if you do Google search, which I've done. So anyway, it's still pretty good. Like if you put my name in, I'm probably the only one you find. There's a salon in Boston, which probably has something to do with Montreal too. Anyway, so that's kind of where that comes from. Anyway, so this class is it assumes you have some kind of background in thermo, I guess, you know, but you don't necessarily need to. So it's going to be basically all like group work. So the groups will be, they're already assigned, they're in Canvas, in Canopy. Right, you guys have used that before? So it's basically like groups of 3 or 4, and then every week we'll have a homework. And usually there'll be like 1 or 2 papers to read. So you have to read the papers and answer some questions about them. So it's like 2 days a week. So the first day I'll go through like whatever the topic is that week. And the topics go like foundations is what you got in your undergrad, theoretically. And then kind of the material stuff, which would be like phase diagrams. A lot of phase diagram stuff, phase stability, the surfaces, kind of like nanomaterials, some iron surfaces. And then some other topics, and finally like computer simulations, you know, and materials modeling. And then I never seem to get to this experimental part of this thing. So let's see, you just came out. You're one of the 9 missing. So it's good that you're here though. You're the best of the 9 missing. So anyway, so there's a web page. If you type my name in, or the 9 missing person, if you type my name into the Google, and like you can find the classes. Go through that again. Type my name in to Google, right? Like that, and then you can put research group if you want, and then it'll come up here, and then just click down. This is this class. But so if you can figure out my name, you can find the class, I think. All right. Is that okay? Anyway, you can ask someone if you can't figure that out, but it shouldn't be too hard. Anyway, because everything's on this web page. It's just like open access. The book is this Chemical Thermodynamics Materials by some Norwegian guys, Stolen, and this Tor Grande, and Neil Allen's an English guy. I was trying to find a book that covered kind of modern topics and materials for materials, and then thermodynamics and for materials. Right, this one seems pretty good. All the books, and there's a bunch of books in here. They're all like kind of coded, so you have to put an F at the end to find it. and then it'll show up. So it's kind of like avoid something, legal ramifications. But the books, most of them are there. Some I got into trouble with that I had to pull off, but none that are that important. Anyway, so this book, I'm following this book. Like I'm basically go through the topics of this book, but I've added some things to it. And then for every topic, I go find a paper from the last couple of years that's kind of useful on the same subject, and then just have you read it. So I think that you'll find out that like if you do research, you're going to learn a lot more from papers than you will from books. So basically, if you find a paper and then you don't understand, and you go back to the previous paper, the links, and you read what they reference. If I keep doing that, so anyway, so I'm going to record all the classes on Zoom, so you guys can pick up, like where you can either watch it from home if you want, or you can come in. It's better if you come in. It's better if the whole class is just you asking questions. That would be the best ideal. Okay, so the more input, even stupid questions, are really good. So any kind of question you have is good. I guess one part of this class, everybody seems to hate thermodynamics. So one part of it is to make you not hate thermodynamics and to find that it's of some use to you, or at least a way that you can access things that are interesting. Like people are talking about something, but you should be able to pick up a paper and read it, and then it's something interesting. So that's kind of the idea, that in the parts of the thermo that you don't know, you can pick apart more or less from what you get in this class, or maybe learn on your own. So somehow to take you from the stage of being an undergrad and then to being a grad student and then being like a scientist or an engineer, so you can pick up anything and kind of read it or put it together somehow, right? So the papers are the best source for that. Books aren't. Books are good to give you kind of what has happened in the past, in a sense, and then really what's important is what's happening right now, and what's going to happen in the future. So like somehow right now is the link between the past and the future. So somehow you have this thing that the papers that are coming out right now are what is defining what the science is. Like what is material science? Pick up a journal and read a materials paper, and that's what it is. It isn't in the book, right? And it's not exactly in the future yet because it hasn't been discovered yet. But so anyway, somehow to try to keep it relevant, I'm trying to find papers that are recent. Anyway, so that book is here, and you can look at it there. I'm not sure if you can buy a copy of this book. I think they give that out free, actually. Like I got this for free by Googling through every chemical thermodynamics materials book, and this one showed up for free. So, but most of them aren't free, but this one is. There's a lot of other books on the webpage. You go to books, and there's a bunch of books, all of that same format. You have to put an F in, like the collective books. Gibbs, Gaskell's the traditional materials thermo class book for metallurgy, and then I think Ragon too, and this is part of Gaskell somehow. There's a bunch of this is kind of interesting book about entropy written by an Israeli guy that you might want to look at. I mean, there's a lot of books here. Chemical engineering thermodynamics is a course I taught undergrad, and so anyway, there's a lot of books here. Kalin's Thermodynamics is an undergrad materials thermal book. So a lot of times the book that I give you isn't the book that you identify with, right? So it's a lot of books. So if you look through, if something isn't making sense and the author isn't connecting to it the way you think, there's like 4 or 5 other books out there. So you should never think that it's you, It's just the author comes from a certain perspective. I come from a perspective, you come from a perspective. So you have to find the guy that's coming from a woman that's coming from the same, and it's somehow close that you identify with what there's like. Maybe you have a historical, like history of science. So there's books on thermodynamics and materials from a historical perspective. And then if you do that, it might be a lot more interesting to you than if it's just someone who's a physicist that's going through tensor equations. And some people, the tensor equations and the history doesn't make any difference. Right, so basically, that's how it is in every subject. So you should try to find as many books as you can find, and then try to find one that clicks with you. I mean, if you're interested in learning it, if you're just doing it because you have to take it, still it's kind of a useful exercise because you can find. I mean, especially in undergrad, I wish they would teach this, because if you can find something that really clicks with you and then you put it on the exam and the guy's like, wow, you're a genius, where'd you come up with it? Because it's totally different from their angle, but you're presenting a new idea, Anyway, but they never seem to teach that. It's always from the one book. But so there's a bunch of books here. And then it'll be it'll be one homework in a PDF format. So that like for instance this week, so the homeworks are here, and then like the old homeworks are here. This is a repeat homework. I didn't make that bold. I should. So it's like this is this homework. It's based on this paper. So the paper's there, and then so everything's kind of here. So it's all in PDF, and then your answer should be in a PDF too. And then you just submit it inside Canopy. Right, and you'll be like homework group 1, 2, 3, and you'll be in one of those groups. And just so that's the format of it. And then every week, so it'll be like Monday. I think it says at noon. So turn it in by noon on Monday. So there's one due this month, like a week from yesterday. So then I can grade it Monday night. I can come in Tuesday, the first part of the class, and go through like what the right answer is, or how. Like usually on Thursday, I'll give you the answer. Like I'll go through the paper, I'll kind of tell you where it's coming from. And like maybe you will or won't understand what I say. So then the point of it is to kind of go back and read the paper and go through the depth that you need to go through to find what you need to kind of answer the question. And you can go back to whatever I said on Thursday, which will be recorded, hopefully, and you can kind of sort through it that way. And then, all right, so usually, so half the class would flunk, if it was just like give you the thing, maybe not half, maybe a quarter, maybe a tenth. So the advantage of having the groups is that like, and then a quarter of the class are like going to smoke through it, or maybe a tenth will smoke through it. So the idea is like so everyone has to get a C or a B probably, right? So basically the people that are not getting it, you can't give them like a C really. A C is like an F in a grad class, right? So everyone's gonna get an A or a B. That's the bottom line, right? And that's the way it is mostly, unless the professor's really a jerk or doesn't like you or something, right? So, I mean, it can happen, but it's rare. It has to be a special case. So anyway, so in that case, like the whole thing is if everyone's going to get an A or a B, and it's going to be hard to get an A, right? But it'll be like you'll get a B. If you kind of go through the routine, you'll probably get a B. So anyway, the idea is that you can kind of learn from each other. And I think that more or less works. And that like I've done kind of surveys, not official surveys, but like talking to the students, and it seems like everyone's pretty happy with it. So that the few people that get an A, so it's different groups every week. Okay, so you get to meet everyone in the class. You can set up a network of people. You can find out who isn't doing anything and who is. And then it turns out like it doesn't matter. In the case where you're going to get an A or a B, I think the same people get an A and the same people get a B, no matter if you do it each individually or if you're doing a group. And the advantage of the group is that you get to meet everybody. And you get to tell like, this person works really hard, I want to hang out with that person, and this person is not even going to show up at all, like totally unreliable. That information is useful to have, whether they get an A or a B, it doesn't matter, but that information is probably more important because later on, they need to use those people to do research or whatever you're doing, and then or even looking for jobs and whatever. So you make a network of people. So it's good to know like who you can trust, right? So that's part of what's going on. Anyway, if someone totally blows it off and you're upset about it. So there's two things you could do. Be like, I don't want to make waves, which is fine. That's what you want to do. And the other is you could like just tell me and I'll just take care of it. What I'll do is I'll give them a 50 for that week. And it's 14 grades, so like 150 doesn't kill you. It's just supposed to be like a wake up call, But like all 50s could be in like C territory, So basically, if you do nothing, you're going to get a 50. All right. So if you get a 50 on the homework, it means you did the equivalent of nothing, which could happen, But basically, it'll be all right, So anyway, that said, the point of this is trying to make you not hate thermo. So I hope I didn't just say that I was going to make you hate thermo. So anyway, so any questions on that business? Or so what do you, is everyone, let's see, how many of you guys are in like had a like a materials undergrad degree? Like 3, and then how many are mechanical? Like quite a few. Chemical. Okay, and what's everyone else?
Material science.
Oh, material science. Okay. Okay. Okay, so what did you do in manufacturing for thermo? It was like machines or something? Or?
It's like 10 years ago.
Okay.
It was for our, not much. We worked more so on dynamics and statics, but so far as thermodynamics, we did work on it. But ours was more close to the book base. So
Oh, look up the steam tables or something like that, or
yeah,
or some of the thermo tables, and then
yeah.
get all right.
So
Chemical engineering does a lot of steam tables. That's why I mentioned that. So it's basically like get the enthalpy change of this process, or figure out what the energy, what's the efficiency of this thing, or something like that. Okay, so the second law you kind of mess around with,
yeah.
like efficiency ideas and things. All right, yeah, it's kind of weird because the field is absolutely completely different in different disciplines. You know what I'm saying? Like it's like you would think you were reading a totally different book. If you pick up a chemical engineering thermal book, you won't understand a word of it. A couple of the words like free energy, entropy are there, but the rest of it is just like alien. And the same with a chemistry thermal book is all about like osmotic pressure and stuff. It's different. Materials is different too. Luckily, like only a couple people have done materials, and what they've done is metallurgy, which is phase diagrams, like looking at these complicated phase diagrams for steel and things. So is that true for the materials people? I mean, that's what I think. So anyway, like Gaskell, if you look at that book. So you might want to flip through, like if you're coming from manufacturing, and just flip through those books at the end, like this. Oh, I think the chemical engineering book might not be linkable, but the Gaskell, Halen, Gaskell. Anyway, you could flip through a few of these books and just see how different the subject is, And each one is completely different. Like a physics class is all about quantum, like kind of quantum mechanics stuff. So they're all like different. The materials kind of takes like almost like takes a lot of those fields together, because you're doing something of an interface area. So in some sense it takes the different areas together, and in some sense it's based on metallurgy. So which is phase diagrams. So but if you're doing research, you're probably not going to do phase diagrams because it's already been kind of discovered, except for like titanium alloys for airplane engines, stuff like that. So there's a few cases where the phase diagrams are like super important, but usually it's within one little fringe area of phase diagrams, and then you don't deviate much from that small area. So it's a little bit like learning the entire thing is, anyway, I'm not that much of a fan of phase diagrams. So my background's in polymers, so I should say that up front. But anyway, so anyway, that's kind of how this goes. Is that okay with everyone? The idea of having group homeworks, and it should theoretically make it easier. And it definitely will guarantee that everyone will walk through with a beat. I mean, I think that's a good thing. So you don't maybe it takes attention off. And with the rotating group, so whoever's a stellar performer, it shows up. Like that week, that group will be like so great. And then you can definitely see who's getting the A, because you can process elimination and figure it out. So because it's 14. So anyway, I think it'll work out okay. And the groups are random, so hopefully that's all right. So I guess it'd be good to people have to be able to get in touch with you from the group. That's been an issue before in the past. So somehow if you can, I don't know if you can give each other cell numbers or something or other. Before somebody suggested like posting them all, and then I got like 5. So I posted the 5, which is kind of weird. And maybe even illegal, right? So, and then, anyway, it didn't help at all because I only had 5. Like, and they were the people that were showing up every week. So the people that weren't showing up who needed the cell phone number, like they didn't get it. So I don't know how to, maybe you guys can just, for the group, I'm not sure how you communicate with each other. Does it have, it doesn't have any email links, right? In the, I think when you go into Canopy, like you can't communicate with the other students, right? Is that true? Or sometimes you can just guess what their email is. That's what I usually do. Can you? Okay, all right, good. So just maybe at first it's like email. And then if people don't respond to email, some people don't use email at all, like, and then they just text all the time.
In my experience, like the Canvas groups, like it takes a while for people to, pay attention to, especially because it's like the start of the class.
Yeah,
So, email is probably the most reliable for that.
okay. Oh, you mean, so you can't access the actual email?
You can like send messages to other people in your group through Canvas.
Yeah,
But like in my experience, people like don't have a good track record of like
Okay.
responding to them.
all right. But you don't have any access to an email, right? To people's emails
I think if you just search on the
on the web.
on Outlook, you should.
Oh, on Outlook. Okay, so hopefully you can figure out. Otherwise, you can just, it's like the first 5, whatever. There's an algorithm for how your email is. It's like 5-3 or something, 6-3, whatever. So the first 6, and if you have a short name, something happens.
If you just type the name of the recipient on Outlook,
Mhm.
sometimes it's true though.
Oh, really? Okay, so hopefully you can communicate. I mean, it'll be a problem if you can't. Anyway, if it turns out like one of your group members, so there's someone that's the head of the group every week, and they're in charge of like kind of being the organizer, but sometimes that person is a person that doesn't do anything. So then the other group members have to figure out what to do. And anyway, just keep me informed if there's something problem, and then like I contact people like quickly, and if there's a problem, like let me know. So hopefully it'll be okay. Maybe I'm just over exaggerating what the problem is. Anyway, so yeah, the notes are here, and then there's like the videos I'll put here, right? And then this other stuff. There's like a bunch of papers, like just papers related to whatever the topic is that week. So you can kind of look through those if you want. So that in some sense, this class is like a prep for the PhD qualifier. So that, in fact, this week's homework was a qualifier question. So basically, the qualifier will be the same format. The question in thermal will be the same format. It'll be like, here's this paper, what are you talking about? So this is kind of like a practice for that. I should mention that too. And the old qualifiers, my old questions are online. Somewhere here's like old qualifier questions for polymers and for thermal. So look at those if you want to do the qualifier. On the qualifier, you need to get a 60. And I just said I give you a 50 when you start. So keep that in mind. See, you're looking for like 10 points. That just shows that you know something, you know what's going on. So it looks difficult, and it's important to have it kind of look difficult to make you study, to kind of put the fear of God into you. But on the other hand, it's not good to just trash people. So the point isn't to trash you, it's to try to get you to like motivate you to try to access things. Right. So, all right, so that's what that business is. All right, so I'm going to just go ahead and go to this whatever's in here. Right, so this first part is like all the stuff you're supposed to know from undergrad, which, I mean, if it was me, like I took 3 thermos as an undergrad, like chemistry thermo, chemical engineering thermo, which there were 2 of it. No, and a physics thermo. The course loads were pretty heavy back then. It was a long time ago. So actually the degrees have significantly weakened since then. But and that's what, and when the funny thing is, when I went to school, that's exactly what the professor said to me. Was that things are so easy now, you know? So it's, anyway, so, but, all right, so I didn't probably get any of this, like retain any of it from it, because it was all just, the engineering parts were just working problems, and the chemistry part was pretty fluffy, and physics and chemistry were too fluffy, you know? So you didn't really get a feeling for like what the topic was, that's a big problem, right? So, anyway, so these are like just a list of terms that they should know what they mean, like homogeneous and heterogeneous. I mean, you don't even need to be a scientist exactly to know those words, right? But so a lot of the papers on thermo, they're talking about a homogeneous system, like single phase, meaning everything's mixed. Right? And heterogeneous means it's multi-phases usually, multiple phases. A phase would be like something's got a different density, it's got a different heat capacity, so it's different in a measurable way, like some kind of definable way. So, right, and then ergodic, non-ergodic. So basically, ergodic means that the system is like searching for different states. So it's on the road to equilibrium. A system has to, all the atoms, say, in the system are like moving around with thermal energy, bouncing around. So they're bouncing against each other, so they can find a place where they're happy together, and then they can match like their true love or whatever is there. Boom. Right. So that's an ergodic system. A non-ergodic system, on the other hand, is like a glass. Like say you have if you have a bag of that, they used to put coffee in vacuum sealed bags, and they were like bricks. They don't do this anymore, but in my past I've seen this. So it's like it's totally solid, right? And that's a non-ergodic system. It's all those little grains of coffee are like locked in with each other, and they're stuck there. That's similar to glass, like all the molecules are stuck there, right? So that system can't like find, it can't find its no, it's like the traffic is bad today and everything. It's like the first day, it's always like a mess. If you don't plan ahead, you know, like it's a mess to try to get in. But anyway, so anyway, a lot of papers will say like this is a non-ergodic, like the problem with the system is it's non-ergodic. It means that like it's stuck somewhere, like it can't reach equilibrium. So if you talk about, this is like bio people like to talk about the free energy space, like for a protein. So you have a protein, it's this complicated molecule, it's got 10,000 or 100,000 grams per mole molecule, and it's floppy, and it's got things like disulfide linkages, or two sulfurs can bond together, or polar groups that want to be together, so it can crowd together, right? So it's got this whole space, and parameter 1, parameter 2 are not defined in these diagrams. So basically, it means like the affinity of one thing to another, or something like that. These are not described in purpose because you can't make this plot in the real world, not exactly. But it's showing that there's a lot of local minima. Like there's a lot of places you can get stuck in a valley, and there's not enough. The thermal energy would be, this is energy on the z-axis. Basically, the thermal energy would be like, say the thermal energy is 6350 KT, and then you would be stuck in this valley because you don't have enough thermal energy to get over that hump. Right. So the idea of ergodic means that you can search everywhere. And non-ergodic means you're stuck in a valley somewhere. You're stuck somewhere. Right. So anyway, that's kind of this idea of ergodic. The word comes from the Greek, like from Odyssey, from how it's linked to that word, like an adventure. Like the molecules are taking an adventure, we can go anywhere they want. That's one word. And then so this is a diagram from the book showing like what they view as ergodic, non-ergodic. So you have like the ground state, right, at a given pressure and temperature. You have graphite, diamond, this temperature and pressure, graphite's more stable, but it doesn't spontaneously, or at some other temperature, diamond might be more stable. It doesn't spontaneously form into diamond because there's a barrier and you don't have the KT to get over that barrier. And then things like buckyballs are at a higher energies. So you always want to go to a lower energy. This is enthalpy, but you want to go to a lower free energy. So they're stuck at this higher energy. Notice a lot of tension in a buckyball. Like the carbon bonds are stretched and bent. So it doesn't like to be that way. It would much rather be flat and form graphite or form diamond. right? So there's a big energy enthalpy change if you do that, but there's a barrier to get to that. So that's another non-ergodic system stuck there, stuck in a non-equilibrium state. And so anyway, so the reason I mention is you just see that in a paper and you're like, what are they talking about? You know, you see like it run into the word ergodic and that's the end of it. So anyway, so metastable, that's kind of a similar thing. Like these are non-ergodic system is in a metastable state, same kind of thing. Equilibrium is what we're searching for. Like in thermodynamics, we're always looking for equilibrium. It means you reach the minimum in the free energy. Gibbs free energy. So something like if this was free energy in this axis, this enthalpy, but then the graphite would be at the equilibrium state for this. Right. So and then there's these things that you should have heard, like extensive, intensive, right? So variables usually, right? So you have an extensive times an intensive, you get the energy. That's kind of the idea, like pressure times volume. So you have volume would be the extensive parameter and pressure would be an intensive parameter. So whenever you always have to have an extensive times an intensive, you get energy. And energy is the thing you're trying to plot. Trying to look at to minimize energy in the system. Right. So you're always looking for two parameters, extensive and intensive, to do that. It could be the electric field and then the polarity of the system, right, to get an electrical energy. So anyway, there's a variety. There's a table that gives all the extensive, intensive variables here. This is from the book too. So the book has some good stuff in it, I think. You know, pressure, volume, force distance, right? So distance is extensive, force is intensive. So there's the extent of length that you traveled. So it's anyway, and then the surface energy times the surface area. So for nanoparticles, you have to talk about that kind of energy. And then electromagnetic, there's a variety. So these can get pretty confusing when you get to papers on electromagnetism, which we'll do. Right, so like electric field, magnetic field, and polarization, magnetization, and those multiplied gives the energy for the system. And then for charges, it's like the charge and the potential. Right, so anyway, so you probably heard those two words in a different context in your undergrad, like some other whatever context, and you probably skipped over and didn't listen to it. So when you read papers, they'll bring these topics up, and then at that point you need to know what they're talking about. So of their own, when they're sitting there, they're of no value, but when you get to that you need them, then all of a sudden they become valuable. So you can understand what somebody's trying to say. Like, why is it that they're looking for an extensive parameter to get the energy when they have this intensive parameter list, right? So they can't get the energy without, they have the, in other words, they have the force, they need the distance that it moved to get energy, because the force alone doesn't have any energy. Isometric exercises don't involve any energy, right? But running down the road does. So if you have to change the distance. All right, so anyway, then state functions is something you'll see. So those are things that, like, three parameters you need to define a state. Or two, listen, not three, you need two to define a state. Like temperature, pressure, volume. Temperature, pressure gives you the volume through an equational state. Right, so you need two parameters to get the entire any state function for a system. Right, so the things we'll deal with mostly are temperature, pressure, volumes 1 over density. Then what? It's all right. Like, oh, I still couldn't hear you, but nothing. So all right, good. All right, free energy, Gibbs free energy, enthalpy, entropy. Right, and there's Helmholtz free energy. That's it. There's some others, but I think that's it, basically. And then first law, second law, and third law. Right. So first law is the energy is conserved. So in any systems, you can do an energy balance around it. So some you lose some heat, right? But basically, energy can't be created or destroyed. Right, that's the idea. So the internal energy is the heat and the work. That sums to zero. But you didn't change the energy, the internal energy. That should be like the first, one of the first things. And then and the work is minus PdV. So you have a extensive and extensive is dV and intensive is P. Those two multiplied give you the energy. Right, and heat is going to be entropy and temperature. Temperature is the entropy is the extensive parameter, and temperature is the intensive parameter. SDT, right, for the Q's SDT. And so each of these kind of energy terms have two parameters that they've broken down into. One's intensive, one's extensive. That's the way this works. But then these things I like to describe as systems. Adiabatic means there's no heat change, there's no heat transfer across the interface. So you define a system as like a box, and then heat transfer across the sides. If it's adiabatic, there's no heat transfer. And then exothermic means it gives off heat, endothermic, it picks up heat. This is like Latin-based words. And then the goal of most of the thermodynamics is an ergodic system that's reached equilibrium. So if you have a non-equilibrium, non-ergodic system, then you're in like kind of never land. But people like to look at non-ergodic, non-equilibrium systems, like classes, right, from a thermodynamic perspective. So we'll go through that a little bit. When they do that, they use these two words like extensively. So it's good to know what they mean for that purpose. Yeah, all right.
What conditions tell the system that undergo the different parts of conventions? What is the criteria for those parts?
Temperature, the paths. Oh, you mean these paths like this? Huh? Okay, so temperature, like this is a scale of energy. So the system, or the entire protein molecule, if you add up all the associations between every component of the molecule, the protein is just a floppy chain. It wants to fold into something like a cell. It's going to form into some object or a cup, right? So it's this long floppy chain, and it has to form a cup somehow. And it does that by these bondings, the disulfide linkages. In polar regions in water, they want to cluster together, or the polar regions want to pull apart, and the non-polar regions, the hydrophobic, want to cluster together. So it'll form like the handle of the cup with hydrophobic groups. So all those things, so there isn't just a two-parameter space, it's all the possible positions of 10,000 or 100,000 atoms or groups within a protein molecule, like amino acids. So to get to that, when it searches through this, KT is moving everything, right? So everything's thermodynamics, the dynamics part is KT. Like all the atoms are moving around all the time, unless you're at absolute zero, which you can't reach. So all the time, forever, everything's moving somewhat. So how much is it moving? Like, can it escape from these little valleys? The only mechanism it has to escape is KT. Like, it has to have enough KT to pop out of that, right? And KT isn't uniform in space, right? So KT isn't a fixed value. Like, you can find certain regions where it's very hot. Even in this room, there's some regions theoretically where it's like 1,000 degrees, like an atomic level, right? And there's some regions where it's almost absolute zero. It's like there's fluctuations in the temperature all over the place. So there's potential for that protein to do anything. Like, nothing is impossible, right, in that scenario. So everything is like moving, and it's getting over these barriers by being subjected to this random motion of everything. That's kind of how it works. So that's why it's thermodynamics. Thermo is KT, dynamics is it leads to motion of everything. And that motion is judged by the free energy. So you use the free energy, and the rule is you want to have the lowest free energy. So all your KT jumping, if it leads to a lower free energy, that's a positive effect, and that reduces your position on this chart. That means you get down into a valley when you reach the point where the disulfides have all bonded and the polar groups have all spread out and the non-polar groups have all clustered together, and then it's formed a cup. then you're down at the bottom of this thing, and to get it to go from a cup to something else, you gotta heat it up. So you're gonna have to heat it so that you can rip apart the disulfide linkages and then pull apart the polar and non-polar things. So that's kind of how this thing would work, you know. That's pretty much the scheme of what's going on. And in order for that to work, also, your system can't be just like one molecule. It has to be a huge system of things moving, because if the temperature is really different in every place, right, and you're relying on that difference in order to reach these wells, then you can't have just one thing that you're looking at. It has to be a huge collection of things. So you look at the average property, like the pressure, the volume, the temperature, because they have no meaning in one spot. The temperature of the room has a meaning. The temperature of one atom doesn't exactly have a meaning, right? Because that's varying all the time. It doesn't have a fixed value. So anyway, so that's kind of how, yeah.
So is the parameter 1 and 2 just means a coordinator of W?
It's pretty vague what it means. This is generally presented to biologists, you know, and they don't care that much about the details. You know, so and basically it's generally an idea of what happens. So you put this into a computer program, right? It's not going to be done with a human mind.
So
because it's going to be,
space there is just for the concept.
Yeah, you have, say you have XYZ of every atom, so 10,000 or 100,000 times, so 300,000 position parameters, XYZ, and a potential energy that goes with each of those potentials. Right, so all of a sudden you're up to like a million things. So it's a million parameters, not two. Right, and that, like, you can't make a plot of that, so they show two. Basically, it's a million parameters, and that's a million parameter space, and you're looking at how the free energy changes across that space and how it's being subjected to KT. So that's molecular dynamics computer simulation. You just put in all those parameters, you feed it into a computer, or a bunch of computers, or a bunch of video cards, and it just churns through it and spits out after a while how it reaches the minimum free energy.
Sometimes I think that in the computer simulation,
Mhm.
in the human size, we can see the only 3 components in one time because our
Mhm.
life is in the 3D.
Well, no, but you're looking at let's say you presented a meeting, you show a video of the molecule folding into a cup, right? So you start with this laggy chain, then it forms a cup, or whatever it is going to form. So you can see them all, so you can understand it. You can't understand it the way the computer understands it, and the way to calculate it, you can't understand. But you can totally understand when you see like a bird flying past you, that there's something going on. I mean, you can see that it went from random, you know, to a fixed state, or something happened. So you can understand it in a different way that the computer can't understand that. So you can give it value, put it that way. For the computer, the cup and the waggy thing are the same. It doesn't care, except in terms of the free energy. But to you, you can use the cup. So I think there's some value in both, you know. Like you can give the computer direction, and the computer can't exactly give you any direction. So it's value for both, probably, you know. It's hard to say which one is more valuable. Like to a computer, like you are such a unique thing, like that you're so valuable to it, right? And to you, the computer is really valuable too. So anyway, I wouldn't devalue yourself, you know, over that. But anyway, so anyway, one of the main themes. Thanks for this. Anyway, so so one of the main themes is heat capacity. Like that's in materials. So the first thing you do is you heat the stuff up, and then what happens? So that's like becomes like one of the main themes in materials thermal, at least from a physics perspective. It's like the Debye heat capacity, and then the Dulong-Petit heat capacity, Debye heat capacity, and there's one other, the Einstein heat capacity. Yeah, so there's like 3 kind of models for heat capacity and materials, and those. So Debye and Einstein won the Nobel Prize. Dulong-Petit, they were before the Nobel Prize. But basically, like those were like some of the seminal works for, so heat capacity is a question people want to know for materials, like for a long time. And so, all right, so I might as well just say like heat capacity right at the start is one of the main things. And if you did like chemical engineering, thermal, you probably get heat capacity. Materials and mechanical, you probably did it too. Manufacturing, not so sure. Maybe you did, maybe you didn't, but anyway, so you have, I mean, we saw before that you had like the internal energies, this heat and this work. So if you talk about how much heat does it take to change the temperature of something, like that's what heat capacity is. So different things, different materials, it takes different amount of heat to change the temperature, right? So some things, like diamond has a high heat capacity, so when you touch diamond to your lip, it's cold. If you take glass, it's warm. So that's how people tell the difference between a diamond and glass, or whatever, cubic zirconia. Right? So basically, you can just tell the lip how the temperature, how it accommodates the temperature change to your lip right from the room temperature. So that change in temperatures gives you this heat capacity, and then there's two ways to look at that. Okay, so we're sitting in a world where like the volume isn't constrained, but the pressure is. It's like we're at atmospheric pressure, so everything we do is at this constant pressure, right? So for that reason, usually the assumption is in experimental work that you have constant pressure. So you talk about the heat capacity at constant pressure. So the two have different values. The other thing is if you're doing a computer simulation, you have the grid usually. So you're going to start with the grid. You're going to put an atom on each grid, and you're going to let them like wiggle around. You have a box that's a fixed size, and you have 100 million atoms in it, and you let them wiggle around. So they have a constant volume that they're fixed in. Letting those atoms, volume changes is easy to do in the room. Like when it gets hot, things expand. When it gets cold, they contract. In computer simulation, that's much harder to do. Right, so computer simulations like this CV term, and experimental people like this CP term. So let's see. So anyway, so you can look at this free energy is dQ dW, and then if you only have PV work, so this only would come into play if you're in a chemical plant and you have like a turbine or something, like you have some other kind of work other than expansion and contraction. So you have shaft work, but generally we're talking about PV work. Right? So the work is this minus PdV, and again it's like intensive, volumes intensive and pressures extensive. So P times V gives you energy, and that energy is called work. Right? If you do like force times distance, it's the same idea. In other words, pressure is force per area, and volume is like length times area, so it ends up being force times distance. It's the same thing. Force distance gives you energy. So that's the work component of the free energy, of the internal energy, right? And then if you say you're at constant volume, then the dV goes to 0, and you just have the Q part. So in that case, du is dq, and dq dt is du dt. So the CV, so it's kind of useful that the V and U are almost the same shape, so you can remember that it's du. Right, CV is du dt, the constant V. So, and then the CP part, if you say you're at constant pressure, then you invent something there. So you invent, yeah.
What's the what will you might use?
Mhm.
How did we get the G minus PG?
This is just to say that there's two kinds of, so if you're doing computer simulations, the kind of free energy, so we're talking about a free energy diagram here, so that the z-axis would be Helmholtz free energy A, if it's a computer simulation, because it's at constant volume. And if it's at constant pressure, experimental, so the actual protein molecule. So the simulation of the protein molecule, this is going to be a Helmholtz free energy. And then the actual experimental, looking at the protein molecule folding, that would be the Gibbs free energy. And they aren't the same. They aren't the same number. Okay, so basically, if you're doing computer simulation or modeling with a grid, like a lattice model, where you put the atoms on a lattice, you have to convert the free energy you get from that. If you want to compare it with experiments, you have to convert it with PV is the thing that converts the two. P times V is the term that converts. Anyway, so like you have the Helmholtz free energy is the Gibbs free energy minus PV. So PV is the term. So if you're doing a modeling calculation of a lattice, and you calculate the Helmholtz free energy, then you can calculate the pressure and volume, and then you can get the Gibbs free energy from that by doing that. Where does this come from? These are just definitions, I think. So in other words, okay, so here's natural to talk about the internal energy, right? So you say internal energy minus this entropic component gives the Helmholtz free energy. And then here something else becomes natural. That's what the point is here. So you have, in this case, entropy is the thing that you invent. Okay, so you invent entropy to accommodate this situation. So entropy is going to be the internal energy be at here plus PV to accommodate the idea that the volume changes here. So you have another term that you throw in. And then if you do that, then you have a change in the you have a change in the free energy. So it's going to be the derivative of this. So this has two terms. You end up with two terms here. Right. And then if you add that in, we're at constant pressure, so this dP term drops out, and then we have PdV, right? From that, so you have dH at constant P is du PdV, and then if you rearrange this, then you can get the Q. So rearranging this, so Q is du plus PdV, so it's just dHP. So Q is just dHP. And then because you're at constant P, let's see, how does this work? The P, yeah, anyway, this ends up being that you can substitute Q for that. Let's see, how did I do this? Oh, this always gets me here. Oh, dQ dt is what we want for C. So you have Q as this because of just this definition of dH. So then you can, anyway, so you can get the CP's dH dt for this. Right? So you have CV, CP, this is du dt at constant P, dH dt at constant P. Right, so, and then the Gibbs free energy goes with CP, and Helmholtz free energy goes with CV. Right, so the point, I guess the point of this is that this is more or less computer simulation, and this is experimental. The two things are coupled together. So then it becomes important if you're going to do computer simulations of protein folding and you're going to do measurements and you want to compare the two, then you want to be able to convert CP to CV or CV to CP. Like there's got to be a way to do that, right? So that's going to involve differential equations of thermodynamic parameters, which opens up a whole nother can of worms. It's like chapter 5 of your undergrad thermal book, right? So and from Imperial's perspective, it's important to be able to do that and to convert those two. So anyway, so anyway, this is the equation that relates those two, right? This is a thermal expansion coefficient. This is the isothermal compressibility, volume, and temperature. So these are things you can look up in a table. So you can actually look up CP, CV, but alpha and kappa are things that are tabulated because you can just measure the change in volume with temperature, change in volume with pressure. Experimentally, you can measure those. So you can get the thermal expansion coefficient, you get the heat capacity, and then you can calculate the difference between these because you're going to do a computer simulation, get CV, experiment, get CP. You want to see if the two agree to see if your computer simulation worked. Then you can measure alpha and kappa, you measure V and T. So that means you can make this thing work, right? So if you have this equation, so where did that equation come from, right? So this is some plots from the book that show that kind of works. So to get that equation, let's see. To get that equation, let's see, we do need, We need to get that equation. Derive that equation. So you have, all right, so this is the second law. So the dq is TdS that you need first. That's why this is in this order. Okay, so the first law is that you have basically you can sum together the energies by any path. Like Hess's law says you can sum the energies of any path to get, like if you're doing a chemical reaction, it doesn't matter if you start, doesn't matter what state you start with, as long as you end up in what states you go through, as long as you end up with the same start and ending states. You can sum the energies and get the same answer to the difference between the beginning and the end, like for a chemical reaction, actually for any process. Right, so sometimes there's an actual path that you go through that's complicated that you can't understand. And there's some paths that you can easily understand. Like say you can take your material and then take it to an ideal gas state. And you know the function to do that. And then you can take it from using ideal gas laws, do transitions, and you can take that state and take it back to your state, for instance, right? So all the free energy changes and enthalpy changes and entropy changes along that path of going from your state to ideal, ideal to another ideal, and then ideal back is going to be equivalent to going from where you are to where you end up, right? So that kind of process makes things a lot easier to calculate. I mean, it makes it possible to calculate. You know, it would be impossible to calculate, right? So that's basically called Hess's law. It's more or less based on the first law, which is that the energy sums, right? In other words, the energy can't be created or destroyed, and it can go through any path to get to any place at the end. Right? So anyway, so it's that business. Then this idea of entropy, right? So the funny thing, like entropy was invented to describe engines, right, by Carnot. And Carnot only lived till he was like 20, and he died of like the plague or something in France. And then when he died, he had published the paper on the Carnot engine. And when he died, because he had the plague, they went in and burned all of his papers, like everything. He was a genius. They destroyed everything he had because they thought it was carrying the plague. Right. So later on, I mean, a couple of years later, this guy Clausius came along and kind of found the stuff that he had published, you know, that Carnot had published, and then figured out that like entropy was defined in that stuff. Right. So historically, it's kind of interesting how things happen. So Clausius got his name on a bunch of things. And Carnot is known for the engine, like the Carnot engine, right? So anyway, so the idea, the second law, which is basically attributed to Clausius, is that for any process you have to like increase the entropy of the system, and entropy is this dq by t. So Carnot invented this idea that dq dt was a state function. In other words, q isn't a state function because you lose heat. So you can't say like I'm going to heat up this room and then like that's going to be a fixed amount of heat, and then later on, so you can't sum the heat over some process like over the day because the heat gets dissipated and disappears, right? So q isn't a state function, right? But s is a state function. In other words, if you can take the entropy at the beginning and the entropy at the end, and then the change in entropy, it doesn't matter what path you took through, but q isn't that way. If you take a different path, you have a different q. Okay, so but if you take dq and divide by the temperature where it was applied, so every step we added heat or took away heat, divided by temperature, that is a state function. So that's what Carnot invented. Like he invented the idea that that would be a state function. And then Clausius realized that that's an important state function because it defines, there's a definition for that state function that always has to increase or stay the same. So if you have perfect efficiency per system, it stays the same. And if any real system, it increases. So you have nothing as a perfectly efficient system. But in the case of a reversible system, then you have this dq, then ds times t is dq. And dq is one of our things that we wanted to know at the beginning, right? You have u, where it is, u is q plus dw, so then q becomes s dt, and then dw is minus p dv if you have no shaft work. So that becomes like the working equation to do anything. Right, so that's the second law of this thing. So you need that to get this thing. You need that to get this. You need to have PDS minus PdV is du. That's just, this is Clausius's term. This is no shaft work. So this is Q and W. And then from that, so you want to know CV's du dt. So you just do ds dt and dv dt, and CV is at constant volume. So dv at constant volume is 0. That's one of the rules. So let's see, dx dy at constant x is 0. Notice if x doesn't change. So if you have a partial differential, this thing out here means it doesn't change, and it's dx inside, then it has to be 0. Right, that should be kind of obvious. This one's kind of obvious, like dx dy is 1 over dy dx. And then dx dx, how much does this thing change with itself is always 1. And then these things are a little bit more complicated, right? But so the others are, you can insert a term into it like dx dz dz dy, if you had dx dy. And then this is an expansion, df dx dx dw. So you introduce this x and y parameters. And then the triple product rules, then mysterious one that just kind of solves your problems. But you can, it shows how to get it. But basically, this ends up being a magical equation that solves everything when you are desperate. Anyway, so you may have seen this stuff before like that, but if not, I mean, I'm not sure how important it is. I won't ask on a qualifier or anything, but basically, you should probably know how to do these differential equation things. And this is the key to it. Those are the things you need to know. Anyway, so anyway, we got this. So CV du dt. So then you can do this ds dt, dv dt, the constant volume because of CV, and then dv dt at constant v is 0, so that term drops out, and you just have ds dt at constant v. So that's a definition of, that's one definition of the CV is in terms of entropy. So the entropy change with temperature of constant volume is CV. In the same way you can do it for pressure. ds dt at constant P is CP. And so here, the HDT, you can write down H. This is the, all right, this is the other thing that's here. So where does this come from? So these differential equations come from this Maxwell stuff, which is back here. So, so this is how this works. So Legendre transformations, like usually a chapter in the thermal book. Anyway, so the way this works is if we have our base equation, and then we can plug in for the second law TDS and PdB. And then so you can say that the internal energy is naturally entropy and volume. And then you can say that du ds at constant v is T, and du dv at constant s is P. And that because, so if you hold v constant, that term drops out. If you hold P constant, if you hold s constant, that term drops out. So you can have these two equations that you use below, or you can rewrite this thing into these derivatives that looks a lot like this expansion thing. So that's the same thing as this expansion. Like you expand something in terms of that. Anyway, so anyway, this is just the expansion of internal energy in terms of these partial derivatives. And then you want to do this to get, in order to get the Maxwell equations, which are going to be these relationships between derivatives of the terms. You take another derivative of that with the other terms. It's dependent on entropy and volume. So you take it du ds with a volume, or you take du dv with an entropy. Either way you can do it. So if you do it the one way, you'll end up with the argument du dv ds, which is this thing, which is P. If you do it the other way, you get du ds, which is that thing, which is t. And then if you take these two things, you get this expression, which is a Maxwell expression. So this is like, these are like magic things that convert one thing dp ds. So the advantage of this is you can't measure s. Like you have no way to measure s, and you want to know how does your system change with respect to entropy. Well, you can't answer that because you can't measure entropy, but you can measure temperature and pressure, temperature and volume, right? So you can convert from that to this. That's really useful, right? So anyway, there's going to be like 6 of these. I guess how many? 6, 4 Maxwell expressions, right? And you can use them upside down. It can be like dv dt at s or ds dp at v, right? So you can never remember all this stuff, right? It's too much. So they have this thing called the thermodynamics square, right? Which is this. So if you can remember that, you can get every other equation in thermodynamics from it, right? So this is kind of a useful tool to have. So anyway, you have SUV, which is a car. It's going to be negative. And then HA, like and PGT, you have to remember it somehow. And the top 2 terms are negative, right? So with that, if you do like a horseshoe of this, if you go like that and down, if you go like this and up, you can get all the Maxwell equations. So ds dv at constant t negative is equal to dp dt at constant v negative. Right, so that they're actually positive. So you have ds dp spt would be vtp. So v sp and vt. Right, so you do these horseshoe thing, you can get all the Maxwells from it. So the reason to do this is that in desperation, you don't have to go back and look it up, you know. So this also has like these differentials, like du dq. Let's see, not that. It's got like u is pdv tds, du is tds pdv minus pdv. Like du is tds minus pdv. So it takes only the minus sign from the beginning one. And a is minus s dt plus minus p dv, right? And g is minus s dt minus v dp, or plus v dp. Right, so it's got all these differential relationships of the thermodynamic parameters in it too. And it's also got the relationship between like A and G. A is G PV, AGPV. So everything is like in the square if you figure out how to get it, right? So it's kind of useful to take that square and just have it so that you can figure things out and add a minute's notice. So I encourage you to remember that thing. But anyway, these are all the Maxwells that you get from that. And again, like you can get all those from this, like TV, TVS, and it's PSV, right? Then TPS, TPS, and then it's going to be VSP. Right, so they're all of the Maxwells are in that square if you mess around with it. Anyway, so what are you doing here? Let's see. All right, so this is how to get this equation. So we got CV's du dt. You use this thing, so you can take the partials and you can get the SDT as CV dt. And do the same thing with H and get the SDT at P as CP dt. And then you need to write a differential for ds as a function of T and V. So there's different ways to get this answer. So one way is to take the S as a function of T and V. So you do this thing of writing an expansion of that thing in terms of 2 parameters. So you can use any 2 parameters. So this is using T and V because that works. Like you can try different things, but that one works. So anyway, so ds dt, the constant v dt. So we have this thing is the same thing as this thing. So that's CV dt. So the first term of this gives the answer CV, and we want to get CP from the other term. So then we could relate CV to CP. The other term is the SDV, the constant T dV. Right, so that one isn't as amenable, but there's a Maxwell for that. So you have ds dv at constant T is the same as dp dt at constant V. dp dt at constant T. So that's useful because this erased entropy from it. So you had entropy, which you can't measure, and you got pressure, temperature, or volume, which you can measure. As you convert from that to that, then you have this thing. So this still isn't giving you like CP, which is what you want. So to get CP, you do a chain rule of this thing, which means that you take so you have dp dt, and you introduce volume, right? So dv dt at constant p, and then dp dv at constant t. So that's how the chain rule thing works. Up here, wherever that is, chain rule this thing, right? So it's, let's see, the negative comes from, I think it, let's see, where's the negative come from? Not sure where the negative came from. Anyway, dv dt divided by, this is a thermal expansion coefficient. So dv dt divided by volume is a thermal expansion. So dv dt times is the thermal expansion times volume. So that's a parameter you can look up in a table. And then dp dv at constant T is the compressibility. That's the dv dp at constant T. So 1 over compressibility divided by volume, so multiplied by volume. Volumes cancel. So this term is just the thermal compressibilities. The thermal expansion divided by thermal compressibility. So you can just plug that in to this. This term is just a number that you can calculate. It's just or get from the table alpha by kappa. And then you have dv and t. So you want to get CP. CP is dH dt. So let's see. So you're going to take the derivative of this with respect to t. So you're going to do ds dt here. So dt dt gives you 1. And then you had the other term dv. So dv dt at constant p is actually the thermal expansion coefficient again. Right, so we have CP, CV, and then this weird thing of the thermal expansion squared divided by the kappa, and then you can subtract off this from that and get that expression. Right, so that's kind of there's a lot of these kind of problems to do, but that's the most important one. Like you can do this for ad nauseum, right? So there's some examples in the book that show like how this could be useful, like so you plot the free energy. This is for aluminum as a function of temperature, right? And it's got 3 phases. It's got a solid, a liquid, and a gas. And you can calculate the free energy of the gas, free energy of the liquid, and free energy of the solid. You always want to have the lowest free energy, right? So if you're at above 2790.8, it's a liquid, like a liquid aluminum, right? And you cool it, gas aluminum vapor. Then you cool it down below 2790, and then it becomes a liquid, because the liquid has a lower free energy than the gas. Cool it down even more, and then it becomes a solid, right? So it's a solid because it's got a lower free energy. And you can overshoot that. You can get a super cool liquid. You can overshoot, kind of get, I don't think you can get a super cool gas, but you can get a superheated liquid. Right? You can get a superheated solid too. So it's possible to overshoot these things, but in equilibrium, that would be a solid liquid gas at those regions, right? So the question is, why does the free energy decrease with temperature? Like you don't have an answer for that, because you would think that as you heat stuff up, like their energy would increase, right? That would just be a natural thing. But here I'm showing you that it decreases. Right? So why is that? So, and also, why is it like lower at some point? Why is it lower for the gas, the liquid than the gas, or the gas than the liquid? Why is that? Right. So, yeah. What?
Because liquid and gaseous phase are unstable.
Yeah, it's unstable, but why? Why is it unstable?
Because as we are increasing the temperature, enthalpy increases.
Right, but so that would be true of liquid and gas, right? Both would increase.
So whenever the going to increase the temperature, the enthalpy with the bonds break. The bonds are going to break.
But no, there's no bonds breaking.
Enthalpy is related to the breaking of bonds.
Yes, yeah, that's true. Enthalpy is related to breaking the bond. All right. Anyway, I'm just demonstrating that this. So anyway, so this experimental is at constant pressure. So if you just do So dg is SDT VDP. So minus SDT is a negative here, VDP. Right, so we have that expression. So we say we're changing for energy with temperature and it's experimental, so we're at constant pressure. So the V part drops out. Then dg is just negative S, and the entropy has to be positive, always. That's the rule of the game, because you can't have a negative entropy. You can have zero entropy in a theoretical world where everything's frozen and stuck. Actually, you can't have zero entropy. It always has to just be positive. So because of that, that's why G has to drop. Right? So in a sense, like, it might be chasing around a cat chasing his tail or something, but basically that kind of explains why the energy is dropping here. You know, because the entropy has to be positive. And then why is it that they have different slopes, like dg/dt's different slopes? It's because of the entropy. Well, it's kind of what you said. The entropy is higher for the gas, right? So it's got a bigger slope, bigger negative slope. And the entropy is lower for the liquid. So if they have a value somewhere, ground state value, then they have to cross because they have different slopes. Then you have to have transitions. See, like this is like a fundamental way to understand the world. Like it isn't just so it's a lot of differential equations, but basically it allows you to get a grip on things that you couldn't answer without it, I think. And so it's kind of a neat thing that this is directly from the book, so I didn't invent that. But anyway, then there's other questions you can answer like that. Oh, it's 250 almost. Huh? Anyway, so there's other things. So I think for the homework, probably not much of this is that important, but it's basically about first law, like phase transitions. But I might go through a little bit more of this on Thursday. What else is in here? Oh, Gibbs Durum I have to go through. What's this thing? Phase of the Oh, the chemical potential. Yeah, we'll have to talk about that. What else? Anything that I missed here? So yeah, I think that's probably good for now. That's okay. I guess any questions, anything, or yeah.
Do you have, you probably already posted it somewhere, I just haven't seen it, but do you have a course, outline list, when our, homework, exams, and things of that nature will be?
Yeah, it's all on Canopy. It's every Monday. A homework is due. That's it. That's all there is. And then usually I have like a final that's like individual, not in a group, which is just another homework.
Okay.
And then that'll be like supposedly like a PhD qualifier question. You can just answer, you know. And then that's it. So it's like every week there's a thing. So it's 13, and then the 14th is like a final kind of. And then you have till the end of finals week to turn that in. Yeah. No, there's no exams. It's just these homeworks, but they're every week. So it gets to be like you got to kind of keep up with it, I guess. I could give you exams if you want, but I think it's better to do this, you know. Like it's the grade ends up being the same, you know. And the cramming, like when I was an undergrad, when I was an undergrad, all I did was cram. Like I would go out and like do whatever, you know, whatever I did, stupid things mostly. Then like a couple days before, or the day before, or the night of, then I'd just like digest everything, you know. And then I'd forget it like the next day, totally forget it. So I'm not sure this is any better, you know, but you know, you can see if it works out for you. In the end, whatever you retain, so it might be whatever you retain, you know, it's kind of hard. No, you think sorry. And I noticed one thing though. If you like a class, you probably don't learn much in it. You know? It's like always I noticed that like the amount learned isn't necessarily proportional to how much you like the class. That's kind of a funny thing. So I remember some classes and like anyway, they aren't the ones that I liked. You know? But then I realized later on they were so valuable. You know? like something was like the truth. Everything's, yeah, this homework is uploaded on the webpage, like so. Oh, the class recordings I'll put in the same place, yeah. They'll be like inside here. So you can see how I did it. Like here, so videos, blah, 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 blah. Right, so it should be like the same place. In fact, you can look at last year's if you want. Yeah.
How do we know our group?
They're on Canopy,
Okay.
Canvas, I think Canvas, yeah. So they're like homework 1, homework 2. In the past, I don't know how you do it, but in the past, it hasn't been a problem. Like I set it up, so. Yeah.
The first homework, I think has like 5 papers, right?
This, yeah, well, it's based on one paper, okay, so. Here. So you can see, this is based on this one paper, like this nature physics paper, which is the first paper. You don't need the other papers, but I put them in, so like this paper is by these people, I don't know who they are. But the first thing he says is that this is his first paper that came out on this subject, which is by this guy, Gene Stanley at Boston University. And he's kind of like Nobel laureate material guy. So the reason why this thing took on such relevance is because Stanley published this in 92, I think. And this paper is a little bit more involved than our paper, because our paper is just, so water, the solid phase is less dense than the liquid phase, so it floats, right? So it's odd in that way. It's like, why is that? That was the question. And Stanley tried to answer it here. He kind of came up with an idea that there's like multiple liquid phases that are in, so you have a dense liquid phase and a lower density liquid phase that are in equilibrium with each other. So I go through this on Thursday. But basically, so this is a paper that you might want to look at if you're interested. You don't need to. In our paper, they're just doing they're trying to show how that high density, low density can come about in a computer simulation. So they look at the topology of something, how you could get high and low density from it. So
what's the idea?
there's just questions, so you just answer the questions. So it's like define a state parameter. Are these state parameters? You know what I mean? So it's a group, so you can work with your group on it. And if you have a problem, you can email me or text me or whatever, whatever you want to do. So I can help you through it. If you totally don't have any idea, just email me.
Do you have office hours?
Usually, but after, so I'll always be here, so I have a class after this at 2, at 3, I mean, or 2, yeah. This clock is an hour off.
So in 5 minutes.
Yeah, so then, after that class, around 3:15, so I'll be in my office,
Tuesdays and Thursdays.
Yeah, so I definitely will be there then. And this 492 roads. So around 3:15 maybe. Probably 3 is good. So but you can just email me. Mostly it's the homework, right? So it's just you can ask the question, but I'll answer it pretty fast. Even if it's just an hour before it's due, or it's at midnight or whatever. No, it doesn't matter. I usually, my phone bings when I get emails, so I usually answer emails right away unless I'm something's going on there. So let's see.
Yeah.
The very first slide, can you please go to the last slide? And the presentation. Just thank you.
My thing is slightly more. That's why I was happy.
Might be slightly. So usually when we try to study about the equilibrium states, we take Gibbs free energy as the reference point,
Yeah,
so that we will also get
Right.
to include configurational entropy to
Right.
understand the
Yeah.
spatial arrangement of atoms.
yeah,
And just know.
this is from the book. I don't know why he put
But
entropy
I
here.
just wanted to ask the question that it will not be wise to stop as this reason why I just told myself to ask at the end of the class.
Mhm.
And I have so we can say it's just because of the textbook, or is there any explanation behind that?
I think he didn't have a, maybe he didn't, maybe he only could measure the entropy here. He's doing the heat of formation or something. So he couldn't get the entropy from it somehow.
So the free energy has entropy playing a very huge, very, I would say,
Right.
very major
Oh,
role.
yeah. Anyway, this is what he has plotted here. So I don't have control of that, but basically I would have plotted free energy, but basically, I think he didn't have the entropy. That's probably why this is plotted this way. It's easy to measure this number, you know. And
So
maybe-
measuring entropy might be a bit difficult, that's. why.
Yeah,
And
that's what I think. I'm guessing, but that's what I think, why it's like that.
can you go to slide number 22?
Can I get your number, man?
Slide number 22. No, 21. Right over here, you mentioned that, so if we take this equation, so did they intentionally put entropy constant over here? Because when we try to apply heat to aluminum, then in that case, when it phase changes, automatically the atoms will rearrange themselves. So entropy has to be differential, but here it is constant.
That's just the definition. That's just the equation for the Gibbs free energy. SDT. I mean, it's a change in Gibbs.
So is this data theoretical or it's based on the
No,
experiment?
it's experimental.
So if it's experimental, then obviously we'll have change in entropy. So I don't know why they use this equation. Or this
I
particular
mean,
relationship.
this is just the standard equation for Gibbs free energy, for the differential of Gibbs. That's a function of temperature and pressure. I can go through where this equation comes from next time, but I've got to get this other thing.
I think you have to run to the next class.
Yeah,
I'll mail you if in case I have any doubts.
All right.
Just go through the. repeat. I have
no,
many
it's a good
doubts.
point. No, I think it's a good point, but I think yeah, it's just where this equation came from. Yeah, that's kind of answered up here, but I'll or somewhere up here. But
And if there's one more doubt I
Uh-huh.
have from one more slide, I just unable to recall. About the Helmholtz energy equation and the Gibbs
Mhm.
energy, compared both of them.
yeah,
I just understood in this way, please correct me if I'm wrong. When it comes to theoretical physics, it's very easy to control the volume while doing mathematics calculations. That's why they use A instead of G.
yeah,
And when it comes to experimental calculation, when conducting experiment, it's very easy to control pressure than volume. That's the
Right.
reason why they.
Yeah, yeah.
You try to say that in the.
That's exactly it. Yeah.
So I'm right.
That's good.
I
Yeah,
was a bit confused whether I'm right or wrong. So I just
yeah,
wanted to make
because
sure.
because how would you change the volume? You know, you'd have to think about like some kind of a diamond cell or something. You know,
And controlling the pressure will be very difficult when we try to put the volume constant.
right? Well, yeah. I mean, with simulation, the volume's fixed, so you don't have a choice. You got really gotta run, but
Oh, okay, perfect.
right.
If I do have any doubts, I'll just mail you.
Okay, all right,
Thank you.
yeah.
I would.
Oh, thanks.
I mean, you're looking. I did in.
I have to shut this down. Where's the turn this off thing here? This is a different, this is in that.
Here you can check.
Okay. Where?
You know, you want to shut down the system, sir?
I want to, yeah, I have to shut down, not power. I want to take my sign out.
Sign.